Greetings. Allow me to introduce you to PuzLock, a research project that focuses on interlocking printable 3D puzzles. Before we move further, let's take a second to orientate ourselves with this diagram. As you can see, interlocking structures are those which can be assembled by solely arranging their component parts in a particular order. However, this can be tricky. This is because generating an interlocking breakdown is a very complicated task. Previous attempts have been either too limited in the types of geometries they are able to process or too computationally exhaustive. However, a method first proposed by Song et al. In 2012 was able to produce results both effectively and efficiently. This method focuses on recursive interlocking, where the assembly of pieces can remain interlocking even after the sequential removal of pieces. We use this algorithm as the foundation of our study, which is split into two categories. The first of which is the implementation of the puzzle generator, which is able to extract 3D puzzle piece breakdowns from a given voxelized input. The second is the realization, which focuses on the voxelization component as well as rendering and shrinking for 3D printing.
We'll now perform a demonstration of our application. All files have been pre-compiled with it being run from terminal. As you can see, the user is presented with a series of prompts requiring the name of the original model, size of the voxelization dimensions, and number of puzzle pieces to generate. Output is provided at each step, showing the user results from initial model testing and resultant puzzle piece values. We can now view the results of running our application. First, let's look at the original solid bunny STL file to use as a reference point. Next, we'll look at the resultant voxelized model using dimensions of 15 by 15 by 15. Finally, I'll show you the resultant puzzle pieces to give you a feel of what an individual piece might look like. Following this, we can take a look at each puzzle piece's ordering and placement by using our dedicated viewing application. Each puzzle piece is color-coded, with the model being able to be fully rotated using mouse motions. The pieces can be iteratively added and removed to visualize the recursive puzzle solution. The viewing application was built using OpenGL in conjunction with other graphical libraries. Finally, let's take a look at the partial disassembly and reassembly of our successful 3D printed 25 centimeter cubed 10-piece puzzle. The 3D printed puzzle is structurally solid, displaying effective interlocking at all stages, providing the validity of our approach. The following table shows the time in seconds to voxelize models, varying in number of vertices and input dimensions. The bottom right value displays a time of almost 32 minutes to voxelize a model with 52,000 vertices and input dimensions of 125 voxels cubed. While this does leave room for future optimization, the results of the voxelizer were deemed acceptable for our project, as any model with dimensions larger than 25 voxels cubed would prove too difficult to 3D print.
Let's take a look at some of the outputs from the puzzle generator. A wide range of geometries can be seen, from a simple cube to a more complex bunny and frog. Notice how different dimensions and numbers of pieces can be specified. For example, the frog at the top right is 10 pieces, while the cube at the bottom left is 100 pieces large. In terms of performance, there are some clear trends. When varying either the number of pieces or the size of the model, we see a complexity of approximately ON log n. Naturally, more complex geometries also yield longer processing times. Should you have any more questions, please visit our page at the University of Cape Town's Department of Computer Science Honors website. Thank you for expressing your interest in PuzLock.